Our first speaker is Nir Lazarovich, who's from the Technion. He'll be telling us about simple lattices in products.
Thanks, and thanks to the organizers. Yes, I'll talk about two joint projects, one with Ivan Levkovich and Alex Margolis, and the other one with my former PhD student, Michal Amir. The title kind of suggests that I'm going to talk about Burger-Moses group, and indeed most of the talk will be about Burger-Moses groups, and eventually this new project is about simple lattices in products of things that are other than two trees. Good. So let's start with what's a BMW group. So the BMW group is a subgroup gamma, the product of two trees. Which acts simply transitively on the vertices. On the, say, vertices of the product. Okay. And we all, I'm guessing we all know the theorem of Burger-Moses. Let's start with that. That there exists a virtually simple BMW. BMW, I think, was coined by Capras. It's supposed to be Burger-Moses and Wise. We also considered such groups and showed that there exists a non-residually finite BMW. Okay, so yeah, so the goal for the talk is I'm really going to spend a lot of time explaining the ingredients of this, and then talk about how easy it is to construct BMW groups once you know what it takes to build one. Okay, and yeah, and the other project I told you about. It's going to be not directly about BMW. Yeah, so how do you show that? Maybe before we go into this theorem, let's maybe talk a bit about BMW groups more generally. So we know that they act simply transitively on the vertices of the product of trees. So we can use this to get a generating set for the BMW group. Right? I mean, pick your vertex in, say, call it O, in the product of trees, and then there are edges going in the T1 direction, and there are edges going in the T2 direction. Okay, and we know that there exists an element that moves you to each one of those vertices. In fact, a unique element that does this, okay, by the assumption of being a BMW group. Okay, and we can call them, let's say, A1, A2, etc., to AD1. Okay, so D1 will be a D1 regular tree. And similarly, you have B1, B2, etc., B2. And as we know, if the graph is connected, you get that the group gamma will be generated by this list of elements. And the fact that the product of two trees is simply connected will actually give us a presentation. Yeah, okay, so here one needs to be a bit careful, and because those elements might be involutions. Okay, so the action is not necessarily free on the product of trees. And in fact, I'll use that because I think BMW groups that are generated by involutions are somehow easier to describe combinatorially. Okay. So let's assume, so I mean, for now, let's just say it's generated by this, but we'll soon talk about the presentation. So here's the, so let's assume that we're talking about, we're called involutive BMW groups, which just means the AIs and BJs are involutions. Okay, so each one of them acts as sort of a reflection along those edges. Okay, and then how can we describe a BMW group? It turns out to be a very easy thing combinatorially. You just take the complete bipartite graph of D1 and D2 vertices. Okay, so let me rewrite it as A1 up to AD1 are one side of the partition, and B1 up to B2 is the other side of the partition. Okay, so I'm looking at the complete graph. And what we need in order to define a BMW, an involutive BMW group, is a partition of the edges of the complete bipartite graph into 4 cycles, and they don't have to be embedded 4 cycles, they have repetitions. They're not simple. Okay, so let me explain how this goes. Do we see yellow? Can you see that it's different from white? Yes. So here is maybe one such 4 cycle, okay? But we see blue. Maybe red. Okay. But I mean, this could be a 4 cycle as well. Okay. Maybe I should call them circuits. I don't know. Combinatoric graph theory is not the strongest side, maybe. But also this. Okay. All allowed. But the only thing I want is that each edge is in one of those 4 cycles and in a unique one. Okay, so really it's a partition of the edges into those 4 cycles. And once you have such a partition, so say P is a partition of the edges of this complete bipartite graph into 4 cycles. Then we can use this to get a presentation. Okay, and the way the presentation goes is we know what are the generators, AIs and PJs. We know it's involutive. Okay, so let's ask each one of them to be of order 2. And for each 4 cycle, the 4 cycle sees 4 of those AI and BJs, and what we have to do is just form them into a 4-letter word. Okay, and this would be A1, BJ, AI prime, BJ prime, where this is in my partition. I mean, and it's easy to see that if you start with a BMW group and you just follow and see what are the squares around the origin, and you gather them into the 4 cycles of the labels that they see along the edges, you get a partition of the edges. But it turns out that starting from a partition, this group that you get here is it describes an involutive BMW group. And the reason is, again, very simple. You just look at the Cayley graph of this thing, okay? Cayley graph where Each one of them is of order 2, so I just treat it as one edge. Okay? Just an undirected edge. So you look at the Cayley graph, and whenever you see one of those relations, you fill it with a square, just a presentation, a universal kappa presentation complex. And what you get is a simply connected square complex in which the link of each vertex is exactly this complete bipartite graph. And it turns out that there's only one such thing, which is the product of two trees. Okay, so we're using the fact here. Unique square complex. Whose links are this thing, and it's the product of two trees. Okay, so now we know how to construct BMW groups, and we see it's a very easy task. Remember that here for those 4 cycles, I can choose just edges. So you choose whatever 4 cycles you actually want, and then if you see that you don't have actual 4 cycles, just add all the edges. I mean, that's legitimate. Okay, but obviously we want more. We want it to be virtually simple, and for that, let me tell you what's the general scheme of proving that something is virtually simple. And it relies on 2 properties. One is being just infinite, and the other is being non-residually finite. So I think that non-residually finite is something everyone is familiar with in this audience. Tell me if not. In general, stop me if I'm not being clear. Okay, but let me define just infinite. So a group, say gamma, is just infinite if it has only, if it is infinite, okay, and it has only finite quotients. Okay, or in other words, if I have a normal subgroup in gamma, then it has finite index. Okay, and here's the basic idea. If gamma satisfies, so I want gamma to be non-residually finite. And I want gamma to be just infinite, but I actually want a bit more. I want every finite index subgroup of gamma to be just infinite. Then gamma is virtually simple. Okay, completely algebraic statement. Let's prove it. It's a one line. I have a long enough line, but it's one line. Okay, let's see it. So the proof of the basic idea is you look at gamma. Inside gamma, you can look at the intersection of all finite index subgroups. Okay, let's call it gamma dot. Okay, we assume that gamma is non-residually finite. Okay, so this is not trivial. Okay. On the other hand, obviously, if I intersect all finite index subgroup, that's a normal subgroup. Gamma. Okay, so since gamma is an infinite, I said one line. Gamma is just infinite. Then we know that gamma dot has finite index. And now the claim is that this gamma dot is our simple simple subgroup, okay? Simple finite index subgroup. And indeed, you can sort of repeat this, or maybe consider what are the possible normal subgroups of gamma dot. Right, so what do I want to say? I know that gamma dot is just infinite. Where is it? Okay, so it cannot have infinite index subgroups. Okay, but it cannot have finite index subgroups, right? Because any finite index subgroup of gamma dot will also be a finite index subgroup of gamma, but gamma dot was the intersection of all of them, so it must be. So gamma dot is just infinite, tells me that gamma dot is simple. Okay, just by, again, analyzing what could a normal subgroup be inside gamma. Okay, so the proof is somehow longer than the statement. Yeah, okay, good. So this is our goal, right? We need to show those two properties about gamma. And maybe as I told you, Wise showed that there exist BMW groups which are non-residually finite. I'm going to treat this as a black box. Okay? Yeah, maybe. There exist non-residually finite BMW groups. So in general, if you want to build something that will satisfy those two, it's enough to take one of those ready-made things that I'm not going to talk about how to prove them, and just embed it somehow into your group, right? Once you have a subgroup that's non-residually finite, the ambient group is non-residually finite. Okay, and the second part, I'm going to use another black box, which is, and again, I should say, this kind of outline of the proof is not the chronological, like historical way in which this was done. Bourget Moses actually proved that there exists a non-residually finite BMW group. And I'm going to use Badr Shalom, but actually for BMW groups, Bourget and Moses proved the version of Badr Shalom. I'm a mistake, but nonetheless. Okay. So here's a recipe for getting just infinite groups, and it relies on the Margulis normal subgroup theorem, or the following generalization of it. So let G1 and G2 be locally compact groups. They're compactly generated. Let's assume they're non-discrete and simple. Okay, the actual statement in Badr Shalom is even more general than this, but let's do that. And let gamma be a co-compact lattice in the product. So just a co-compact discrete subgroup of this product. Okay, and I want it to be irreducible in this product in the following sense. So I have the projections of gamma into each one of the components, okay, and I can project gamma to each one of them, and what I want is the projection to be dense, such that with dense projections. Okay, then gamma is just infinite. Okay, and the proof, I mean, I'm going to treat this again as a black box, but it's not, I mean, the proof of this follows the sort of ideology of the proof of the Margulis normal subgroup theorem, in the sense that we prove that any quotient gamma mod n has to have property T and be amenable and hence finite. But okay, it's a much more general setting. Prof.
I have a question.
Yes.
So if you suppose that G1 and G2 are the automorphism group of T1 and T2, the statement
Okay.
this generality is contained in the Moses?
So let me remark, I mean, you started great, and then I'll tell you what Boolean was with. But yeah, yes. If G1 and G2 are certain groups in the automorphism group of the trees, then the statement was in Boolean. Yes, so let's actually say something about this, because I mean, it seems very natural. I mean, I started with like a BMW group is gamma inside the product of two groups, okay? And they're definitely locally compact, compactly generated, non-discrete. They're even almost simple, okay? So they're virtually simple. So let's say this is a theorem of Tits that out of T is a, say, D-regular tree, is virtually simple. Okay? In fact, we know exactly what is the simple subgroup. It's called odd plus, and can be defined as the group generated by fixators of edges, or alternatively, it's just the group, the subgroup of odd T that preserves the coloring of the what do I want to say? The bipartition of the vertices of the tree to two colors. So this has index 2, and this guy is simple. So this is it's generated by all the fixators of edges. So this means pointwise fixators running over all the edges of the tree. Okay, so this guy is simple. Okay, so I mean, and gamma is a co-compact lattice. Okay, but here's the problem. The problem is it cannot have dense projections in odd Ti. Yes, so that's and the reason for that is that the vertex stabilizers inside odd T are not topologically finely generated. So it's something you need to have those dense projections. Okay, so here's what Burger and Moses did to fix it. They looked at smaller groups inside odd T, okay, which are still locally compact, compactly generated, etc. Okay, but and showed that and found BMW groups with dense projection into them. Okay, so let me say what are those groups. So can I use this board, or do you know this stuff already? You're the only one. Okay, so the groups that we'll actually need to define are called universal groups. And I'll define a particular instance of a bigger family of groups, but the one that will be relevant for us. So yeah, so here's the idea. So you take your tree T, okay, let's assume it's a D-regular tree. And you fix the coloring of the edges of the tree with proper coloring with D colors. So coloring. Okay, so let me maybe do a drawing here. So here is D equals 3, and I pick a proper coloring of the edges of this tree. Okay, what this allows you is to define what I like to think of as the derivative of an isometry of an automorphism of T at a vertex. Okay, so if this is a vertex V, and I take some G in T, I can define the derivative of G at V to be what? So G takes the vertex somewhere. Okay, let's say here. Okay, and it takes the edges around this vertex to the edges around this vertex. And by comparing what happens to the coloring of those edges, I get a permutation, okay, on D colors. So DVG is exactly this permutation on D colors. Yeah, it's a derivative because it tells you locally, right, what G does in a neighborhood or in a germ. Good. And I can define the universal group. So let me call it just U. In general, one can, okay, let me define it and say what's the more general definition. So the universal group will be all G in odd T such that the derivative at every vertex is in the alternating group. Okay? More generally, one can define the universal group of some subgroup F of SD and ask this to be in F. Okay, but let's just do it for the alternating. And I think intuitively, this should fix the problem because, so I didn't really tell you what was the problem with .t. I told you, yes, sir.
What's the history of the groups that you just defined?
These were defined by Boger and Moses. There are a series of, yeah. Yeah, but what I didn't tell you here is that the issue with RT was, this I did say, the fact that the stabilizers of vertices are not topologically finitely generated. Okay? And the reason is that you have those signs of permutations that you can have at different spheres. Okay? And by restricting to the alternating group, you can, at least this restriction you take away. And now you can hope. Okay? And okay, so
Sorry, can you say again? Can you just try to explain why if you drop this condition, it's not topologically finite? Is that what you just tried to explain?
the issue, or the way you show that it's not, that OT T is not, or the vertex stabilizer in OT T is not topologically finitely generated is using signs of permutations. So by taking this away, at least this point doesn't work, but we'll actually see that it's, that it is topologically finitely generated. In fact, you can find a BMW group that lives in this product of universal. Yes. Good, so yes. So let's maybe discuss how can we show that something indeed projects densely into universal groups instead of the orthogonal. And this is a theorem, again, by Burger and Moses, which is sort of a local to global phenomenon that, which is, I mean, in my opinion, the really a remarkable thing here, which is just by knowing that a group is, well, vertex transitive, that's a global condition, but locally satisfies what you want it to, so it looks like U locally, then globally it is actually dense in U. Okay, so let's say if G inside U satisfies, so U is now a universal group, okay, for, let's say, for a fixed tree T of degree D, and I take a subgroup, and I want it to satisfy, first I want it to be vertex transitive, so G acts on the vertices of the tree T transitively. Okay, so a global condition, and now, which is actually also a local condition if you think about it. And I want it to, so around the vertex, if I look at the stabilizer of a vertex in G, and I consider what is the derivative of this at V, know that for this group, dV is actually a homomorphism. Then I want to get all possible alternating, all possible even permutations. Okay? And let me add, okay, let me add another global condition, but in fact this could also be turned into a local one by their work. Let's say G is non-discrete. Okay? It's not really necessary, one can replace it again with a local condition, but let's just say this. Then G is dense in. Okay, so this is something, I mean, quite remarkable, just by knowing that it's vertex transitive and that it does what U does in a, you know, at a vertex V. Okay, this could be any vertex. You know that it is, in fact, universal group. Okay.
Could G be discrete?
Sorry?
Could G be discrete and satisfy 1 and 2?
So G could be discrete satisfying 1 and 2, but, okay, so here's, you're insisting on me giving the actual local condition that's needed. So the local condition that suffices instead of asking for it to be non-discrete is to look at what G does to a ball of radius 2 around V, and not just the ball of radius 1. And if it does what U does on this ball, then it's also then it's not discrete. Okay. Yeah. So now we're at the point where we can put those pieces together and construct BMW groups. I hope I'll have time to say something about the proof of this local to global maybe later on, but let's just try and piece those things together and see how to construct BMW groups, given those 3 black boxes. So we saw, I mean, in order to construct a BMW group, I just need to give you some partition of this complete bipartite graph. And now let's ask ourselves, like, what can we say about the projections of such a BMW group to each one of the trees, okay, in the product. So maybe, yes, let me draw. Yeah, so first of all, maybe I need to tell you what is the coloring, okay, on each of the trees. But for this, I can just use, let's fix a vertex for O. Remember, I told you you can label those edges by A1, A2, up to AD1, right, the generators. They're involutive, so I'm just going to disregard the orientation of this thing. And this gives me a coloring of the entire fiber tree T1. Okay, and similarly I can do for the tree T2. And now what are the elements of gamma that fix the vertex O when I project them down here? Okay, they are exactly the elements that go in the B direction. Right, so each element of B, for instance, give me something that when I project down will fix the vertex O. Okay, so this will allow me to compute what is the local action at V, at O. Okay, and what is it? So I'm going to cheat a bit. I'm actually using the fact that it's involutive here, but in a way that I'll not say. So here's, say, Bj. Okay, Bj and A1, say, or A, let's call it I, belong to some square. Okay, and this other side of the square is labeled by something, I prime. Okay, so from this, meditate over this for long enough, you see that the local action of Bj at O is actually the one that sends AI to AI prime. I mean, I'm lying, but it's involutive, so it's fine. Okay. So DO of Bj, or the projection of Bj, will send AI prime or I prime to I, or I to I prime. Whatever. Yeah, I think that's the correct one. Okay, so by choosing those cycles, I mean, what does it mean here? It means that if I look at Bj, and I want to know what is the permutation, well, the Bj is connected to 4 cycles to some AIs, and what it does is just permutes or transposes the AIs in which it shares a cycle. Okay, so it's an information that you can read from this very easily. And the only thing you need to check about it is that it generates AD, which is sort of the generic situation, right? So, the works of Dixon. Okay, I don't remember the years, but long time ago, show that if you just take 2 random permutations in Sn, they generate Sn almost surely. Sn goes to infinity, and this was extended by Liebeck and Shalev, who show that if you take 3 involutions uniformly at random, they generate either Sn or An, also for Dixon, either Sn or An, almost surely. Okay, so the generic situation is that you pick some involutions, they're going to generate AD. I mean, it's not difficult to. Okay, so finally, let's construct virtually simple BMW groups. Let's even do it here. So the first black box was that there exists a non-residually finite BMW group. Okay, it's some fixed thing of small size, whatever you want. Pick it. Okay. So it's gonna choose for you some 4 cycles on a small portion of a small complete bipartite graph. Small here being less than 6. I think it's even enough. Here I forgot to say something. It's important. You want some simple groups to appear also in AD, and you actually want AD minus 1 to be simple. Okay. So you do that. That's your non-residually finite BMW.
Excuse me?
Yeah.
So you're saying that this non-residually finite one appears with the same construction that you said before, like with involution?
Sorry, which?
You're saying that this non-residually finite black box one also appears as with the construction that you said before, like choosing 4 cycles of involution.
All BMW groups. I mean, okay, I restricted myself to involutive. I should have said there exists an involutive non-residually. But yeah, all of them come from this, have such a presentation. So, yeah. Okay. Now we don't necessarily know that they generate AD. Okay, so let's just add, more of them so that connect them with 4 cycles so that they generate AD. And in fact, using only, as we said, only let's say 3 of them, I can guarantee that the BMW group, as long as big as I want, degrees big as I want, will satisfy the second condition. Okay. So what do we get? When we look at the BMW group generated by this gamma, we know that it contains inside it a non-residually finite BMW group, so it will be non-residually finite. We know that, when we look at its projections into each one of the trees, definitely will act transitively on vertices because gamma did on the product of trees, okay? We just guaranteed that it will have the right local actions. And actually, the fact that it's non-discrete will follow from the fact that we have embedded something that's non-residually finite, right? I mean, if this action was discrete in the trees, then what we'll get is something that's virtually a product. So a product of a lattice in one tree and a lattice in another tree. That's definitely residually finite. Okay, so we got it somehow for free, this third point. But okay, if you don't like that, you can just, as I said, check a bigger local condition. It's also possible. And so what did we get? We get that this is non-residually finite plus has dense projections into the universal groups, let's say U1 and U2, okay, corresponding to the 2 trees. Note, by the way, that here I wanted something that's, okay, let's say dense projection to those. What I did not say is that we put it there. This U plus is simple. Okay, similarly defined. Okay, and it's just exactly the same as the proof of things. I mean, it follows. Okay, so these are virtually simple. So, yeah, so gamma satisfies this, and so it's just infinite by Badr-Sharon. Gamma is just infinite. But actually, we know more because, we wanted more. We wanted every finite index subgroup to be just infinite. But any finite index subgroup of gamma will project to finite index subgroups of those UIs. But UI is simple. It doesn't have finite index subgroups. Right? So the same will be true for finite index subgroups of gamma. By the same argument. Okay, and then by this basic sketch idea, gamma is virtually simple. Okay. So now that we know, I mean, up to a lot of black box, how to find BMW groups, we note that, I mean, looking at this, that we only had to choose a very small portion of this data. And a lot of it is left for us to decide on, like, how to complete. And this, in fact, shows that there are many BMW groups. So this is maybe the result with Lefkowitz and Margulis. Yeah, so there exists alpha and beta such that the number of BMW groups of degrees, say D1 and D2, even up to abstract commensurability. This may be more interesting than just counting them. Is bounded between D1 and D2 to the alpha. And similar thing with beta. And I basically told you all of the proof. The proof is just count how many ways you have to complete this diagram. Okay, modulo that I didn't explain how to get the abstract commensurability. So here the idea is really that the number of, not just of BMW groups, but of virtually simple BMW groups, as we saw, can be bounded by those STIs. And moreover, you can control the index of this subgroup to be exactly 4. 4 coming from plus in one tree and plus of the other tree. Okay, so, and this uses, I mean, here one needs to put some non-residually finite BMW group, involutive BMW group, and one in which this index is controlled was given by Radu, and we use this one. Yeah. Okay, so this is one result. And now, in the remaining time, let me tell you what we did with Michal. So what we did is construct virtually simple groups in products of a tree and a Davis complex. Okay? And so let me define for you the objects you want. So the first thing is it's an odd graph. OD. The odd graph of degree D. Yeah, so what is it? It's the graph whose vertices are all the subsets of size d minus 1 in a 2d minus 1 set. And edges are just disjoints. So A is connected to B, and they're disjointed. Okay, so for instance, O3 is the famous Peterson graph. Okay, so these are all subsets of size 2 in a set of size 5. 1, 2 will be connected to 3, 4, to 4, 5, and 3, 5. Okay. And so let's maybe call this just L for now. I'm not going to drag the syntax. And given a graph, we know how to construct the right-angled Coxeter group corresponding to this graph. Okay, so WL. And should I write down the definition? No. Good. And the Davis complex. Okay, so this is the right-angled Coxeter group. And we have the Davis complex for XL. Okay, so here's the theorem. So there exists virtually simple co-compact lattices, or maybe I should just say simple. Simple co-compact lattices in out of a tree. Okay, so this is the D regular tree as before, and out of X. I mean the D is D1, should be D2, whatever. For some big enough D1 and D2. Okay, so yeah, so the idea is the same. I mean, you want to produce a co-compact lattice in a product. I just erased it, but use Badr Shalom to show that it's just infinite. You try to embed some non-residually finite thing inside. Okay, but again, what's kind of missing is a version of this, a notion of universal group, right? And some local to global theorem that would work for that. So note that on one of the projections, on the tree side, we can just use Burger-Moses universal groups and the local to global thing we have there. There's nothing new needs to be said there. But on this side, okay, one needs to define a universal group. Okay? And yeah, so let's do that. So really the property of, I mean, if we look at this Davis complex, what is the Davis complex? It's just the Cayley graph of WL, and you put some cubes to make it simple. Whenever you see the one skeleton of a cube, you put a cube. So naturally, the edges of this thing come with the labeling. Okay, the labeling of what? So let's say the links, well, the edges. No, that's right. Edges of this are labeled by what? By vertices of L, right? Okay. Or maybe a better way of seeing it is instead of looking at edges that we did here, we should have thought of the link of a vertex, right? The link of the vertex tells me the local structure around this vertex, and the links of XL are exactly the odd graph L. But the important thing is that they come with a particular way of identifying links in here with L, okay? So now I can just, I can define a derivative as I did before. So for G in out XL, I can define a derivative of G to be what? You look at the link around V, and you see how it maps to the link around GV. Okay? those are identified with L in a fixed way. So this gives you some automorphism of the graph L. Node graph. Okay? And here's an interesting fact. This follows from the Erdős-Corrado theorem. The automorphism group of the odd graph is exactly the symmetric group on 2D minus 1. Right? Obviously, if I permute the set here on 2D minus 1, I permute the vertices and I keep the disjointed relation. So obviously, this is inside here, but actually there is equality between them. And this allows us to define a universal group, right? I mean, universal group will be exactly the same definition. So all G such that dVG is in the alternating. Okay, so this gives us a universal group. What we do, out of time, so let me just say quickly, we prove a similar result of local to global. If I had time, I would have explained how this uses transitivity of the action of a stabilizer of a vector of a vertex on the spheres, which does not exist in this new setting. Okay, so there's some elements of this that really had to be revised. But nonetheless, we get some local to global result, and using that, and let me also mention briefly that just as for product of trees, XL is the unique cube complex with this link at each vertex. But what's more interesting is that XL times T is the unique complex with the link L join a finite set. So really just defining the local structure tells you that you get a lattice acting on this product. That's yeah, okay, let me finish here. Thanks.
Questions?
Do you do out XL times out XL?
I mean, in principle, yes, you just need to construct something. I mean, it gets, just combinatorially, it gets more difficult. Yeah, but in principle, we already have all the ingredients for that. You just need to come up with a construction, just to work out the combinatorics of it.
Box.
Sorry?
So you don't know how to do the black box, or?
No, it's not the black box. It's really just coming up with the. I mean, in BMW, you just need the 4 cycles. Here, it's a bit more involved to check that the link is that, and you actually get something that defines a cube complex. So you need to come up with a combinatorial construction for that.
But how do you get the non-residual finiteness?
The non-residual finiteness you get from, I mean, if you look at the hyperplane in XL, it's a tree. So you get a 3 times 3 inside. And inside that, you can embed the existing black boxes.
So I guess your ODs never have 3 cycles, right? I guess that just is a fact or something. So
Yeah, that's true.
So is there any candidate or possible XL you could try to do that's more than 2-dimensional that might?
Yes. So I mean, I have to think about what's exactly the right number to put here, but you can change 2 to something else. I think it's just change this to M, but maybe I'm wrong. And you get something that's higher dimensional. The problem is once you do that, you also get squares, which this doesn't have.
Yeah, right.
I mean, the arguments are very 2-dimensional in our paper, but I don't think they actually need the fact that it's 2-dimensional. Like it doesn't seem essential.
So when you, in this process, when you pass to a finite index subgroup that is simple, do you always get rid of all the torsion?
Oh, it's a very good question. Yeah, so, I mean, this is like a potential example of a simple group of cohomological dimension 3, which is, I mean, we only have examples of 2 and infinity because of torsion. Unfortunately, just the particular combinatorial construction that we get has WL inside it. And when you pass to this plus, the finite index thing, this still has a little bit of torsion left. It's unfortunate, but I think it's, I don't see a real intrinsic reason why you should not be able to build such an example using this.
And how about in the first theorem? Like those you said that they all have an index for.
The index 4 is doesn't have torsion.
Doesn't have torsion. Okay.
Okay, I can tell you exactly what's the torsion. Yeah, maybe it doesn't have.
Okay, great. Let's thank Nir again.